Hi, I'm Liu Our group is Group 16. Our title is Automated Car Battery Predictive Maintenance System. These are my group member names, student ID, and courses. I'm going to talk about the background of the Automated Car Battery Predictive Maintenance System. It's a system that manages the car battery condition by using the trader model to predict the battery condition. So after it's predicted, it will inform the user about it if the car battery is in low voltage condition. So the general meaning of the predictive maintenance tool is to forecast the event and calculate what time the failure will occur. Then it will alert the user to take the corrective actions such as maintenance or repairing service. It's a condition-based maintenance where it needs maintenance by monitoring the condition and performance of the car battery in real time. It will predict the car battery when it should be changed before its breakdown. So with this function, it can reduce the likelihood of failure. So with this in sensor, IoT, Internet of Things, machine learning, data analytics, and modeling, the predictive maintenance will determine whether there is any warning sign of the car battery. So if there is warning sign, it will tell the user to schedule the maintenance and to repair or change the car battery. So if without this, the user is not able to know whether the car battery is in normal voltage or low voltage and does it need to change with a new car battery. So with predictive maintenance, it can lower the frequency of maintenance and prevent the unplanned reactive maintenance without incurring costs of maintenance and time consumption. It uses historical and real-time data of car battery to anticipate the problem. So with the IoT, it allows connection and communication between the machines. Sensors are able to connect to the system to capture, collect, analyze, and send the real-time data to IoT. So it will send the data into the Lambda function for the prediction with the trader model from the same maker there and send the result back as alert message to tell the user if the car battery is in low voltage. So the service center will be notified too. Is to reduce the unplanned downtime and costs by providing the quick estimate before the car battery is dead. So the goal of the predictive maintenance are able to predict the failure before it occurs, schedule the maintenance at the most efficient ways, allow the particular of equipment lifespan to be optimized to its fullest, but not after the equipment has been compromised, and prevent the failure and unexpected breakdowns compared to the traditional method of maintenance. Thank you.
Good morning to Sir and friends. My name is Sananji and my student ID is 2000147. Today, I'm going to discuss about the history of auto mechanics, which has led to our AWS project team as we want to make an automated car battery anomaly detection system. So, in the late of 18th century, the early European automobiles were advanced by automotive engineering, but compared to American automobiles, they have not created a standardization for the automotive maintenance and repair services. And this is a photo of Henry Ford, which is the founder of the Ford branded car. He was credited with perfecting automobile making with better efficiency, standardized the car parts, allowing them to be reproduced in the production line faster and in cheaper price. So I'm going to wrap up what have happened, what have done in European automotive mechanic history. So in Europe, the car makers has been the auto mechanics itself as well. And also there were certain lucky upper class men who own the cars, having the driver who have specialized knowledge in car repairing. And there is no standardization in automobiles mechanic maintenance. In American history, they have standardized in car parts making and also as well as the automotive mechanics maintenance. And thus, it has making the car parts making standardized car parts making being have cheaper price and faster car parts making for the standardization itself. And they have more dealerships and private companies who have offered the mechanic services as demand increases because the car part making have been cheaper and also be faster in making. So the advancement of automotive mechanics maintenance that have brought by those European and Americans in the worldwide, which in the mid-century of the 19th, the auto body and auto mechanics were split to better resist market stagnation. Thus, from their onwards, automotive repair industry have been advancing until today with the advancement ICT and continuing to go. Thank you. I'm going to pass it to the next presenter.
Good morning, everyone. My name is Ranjana, and now I will talk about the challenges. So the challenges of IoT, the first one is data acquisition. We need to decide what kind of data is needed to solve the problem. The next challenge is data ingestion. How do we move the data from the edge to the cloud? The last challenge is the module deployment, where to host the model inferences in for the solution. So for the challenges of machine learning, first is defining features. We need to define what is the problem statement. Then choosing the right algorithm. We need to have clear understanding of the data and the problem. The last one is model maintenance. We need to have backup plans and solution to retrain the model as the new data flows in and predictions, and also when the predictions are incorrect. So now I will talk about the future trends and improvement. So in our solution, we are applying CRISP-DM, which is cross-industry standard process for data mining. This is a model for finding patterns and trends in a data set. So first, the problem statement is defined in business understanding. Then we need to evaluate the data to understand it. Then prepare the data and configure the data to properly train the machine learning model. Then the model is trained and the performance is evaluated. Finally, the model is deployed to a production solution. However, this model can be modified and completed into a flywheel by adding more steps. So this flywheel is signifying the process of retraining the model after it is deployed, because the model may experience some flaws in about the parameters of the devices or the environment. Then the model can be continuously retrained and optimized. Then during the process, new inferences can be made so that the stakeholder can learn more and learn new things about the business and explore more new opportunities in the market. So if we have more knowledge and cost, actually we can also improve our proposed solutions. So we can use IoT Green Glass to analyze the data closer to the source, and it is hosted by EC2. Then we can also use AWS IoT Analytics to act as a cold storage to store historical data for model retraining. So the train model is stored in the Amazon S3 bucket, then it brought into the IoT Green Glass and to be redeployed. So it is available locally with the Lambda to make inferences from the model. So we also use AWS IoT Core Events. So it acts as a complex event detection service. So if the model is underperforming, then the model will send a notification to alert the respective parties to retrain the model or perform some kinds of operation, for example, maintenance activity.
Good morning, everyone. My name is Easier, and I will be proceeding with the problem statement and objectives. Over the years, traffic accidents that are not derived from human errors have seen an increase in numbers by the increasing number of drivers on the freeway. The majority of these accidents that are devoid of human errors are caused by faulty components that are checked in the vehicle, probably due to the lack of maintenance or simply the manufacturer's outlier error. As such, it is always important to check and determine whether or not the vehicle's components in question are in good health before heading to the road. However, a vehicle owner might not have the appropriate experience or skill to initiate a full vehicle health check and may leave some components under the light. In theory, the vehicles can be checked by a skilled mechanic every time it could be used on the road. However, such solutions are deemed impractical. With that said, it leaves us with the problem of initiating a full vehicle components health check and fault detection without the need of an immediate skilled personnel under practical sense and common usage in everyday solutions. The main objective of this project is to solve the overarching problem as stated, the problem of initiating a full vehicle health check without the need of a skilled personnel. The objective can be further divided into the further sub-objective. To obtain the component statistical data and the current condition without the need of an experienced personnel, for instance a mechanic, to determine and check whether or not the following obtained component data have anomalies within them, which would indicate a faulty component, and to notify the vehicle owner of the anomalies detected via accessible communication means such as emails or SMS.
So now I will continue to talk about our proposed solution. So here is the architecture diagram of our proposed solution. So in this diagram, there are 4 modules. So now I will talk about the first module, which is the IoT module. So we have using the AWS IoT device SDK, and we chose Python for it. So this it actually helps us to connect IoT devices to other AWS IoT services by ingesting the data needed. Then we also use AWS IoT Core. So this service enables us to connect the connected devices to easily and securely interact with other cloud services. So it helps us to collect the data from our stimulated sensor, which activated and by the help of the devices SDK. Then it will send the data to the other service, which is the Lambda, to trigger the train module. So now I will show you the configuration. So for downloading the AWS IoT device SDK, we need to follow the necessary steps. So for example, we can follow the step in GitHub to install the necessary requirements. After that, in our AWS console, we go to AWS IoT Core management console. So first we create a policy for the device. So it will allow us to control access to other AWS IoT services. Then we go to the thing to create a thing, which is create a device. So during the configuration for this device, we actually need to download the certificate, the private key, and also the public key of it. Then we attach the policy we just created into it. So then, for example, so we download the certificate, the private and public key in a file. Then we create another publish file to activate the stimulated device with the help of the SDK. So here is the code. We need to then this is the SDK we installed. Then we put in the necessary information, for example, the certificate, the private key, and public key. Then here is the data needed, for example. Then we need to publish it into a topic. So in the AWS IoT management console, we need to go to the test. Then we need to subscribe a topic. So here is the topic we created. So we need this. So this data will sent by the MQTT protocol. So now I will show you how to publish the data by using this Python command. Okay. So now the data is published into the cloud. So here is the data. So then the data will trigger the Lambda, which also stored in these rules, okay, to trigger the train module.
Hi, I'm going to briefly explain about the machine learning module. Amazon SageMaker is a cloud machine learning platform that enables developers to create, train, deploy the machine learning model in cloud. So Amazon S3 is a simple storage service that offered by the Amazon Web Service that provide object storage through web service interface. It can allow the user to use it as a storage for internet application, backup, and recovery. So Amazon Lambda is a serverless event-driven compute service that runs code virtually without provisioning and managing the server. It can trigger over 200 AWS service and software. So now I'm going to demo this machine learning module in AWS. Hi, I'm Liu Wenxun. I'm going to talk about the AWS Lambda, SameMaker, and S3 bucket with storing the example dataset. So first we move on to the SameMaker right here. So we need to create a SameMaker domain to have a SameMaker environment. So we will move on to the Jupyter Lab. So we already code the model. So before that we have to import some important library right here, and then we need to call the dataset, the example dataset from the S3 bucket, which is named right here, and then the dataset will be called. So these are the column in the dataset. So we remove all the users one and then remain the useful one. So the data that we remain is current, resistance, voltage, and battery condition. So these are the function and the graph for the analysis purposes. So then we move on to the x and y. So x will be storing the current, resistance, and voltage column, and then the y will be having the battery condition. So x and y will be used in the text split function right here, and then split it with the 0.3 right here. And then we'll be using the XG boost model to train the dataset that we already split, and then the accuracy will be calculated right here. But before that, it will be generate an endpoint name right here. This endpoint name is used to call this model from the lambda. So next later we'll talk about it. So these are the accuracy score, which is 0.96667, which is around 96.63%. So these are the SameMaker code, and then these are the S3 bucket that will be storing the car info CSV that we said just now for the example dataset, and then car info dataset will be storing the data and attributes model from the Jupyter Lab. So in the lambda function, we'll be having a Python code right here to call the endpoint name that we said just now that we correct, and then we have the IoT core dataset. IoT core will be pump some data into the lambda, and then the lambda will be predict the data from the IoT core there, and then the result will be stored in the S3 bucket right here, which is called result right here. So that's all for my part. Thank you.
Thank you. So I'm going to talk about this dashboard module from our architecture diagram, where this AWS S3 bucket, it provides us the object storage from the processed data from Amazon SageMaker. Well, it will send the data into the Amazon QuickSight, where it is a fully managed cloud-scale business intelligence service that is powered by machine learning, allow us to create the data visualization and dashboards of our car info. Good morning, sir, and reference. My name is Namji, and I'm going to continue about the dashboard in our architecture diagram. Firstly, I will introduce about the Amazon S3 bucket, where we can click here the buckets. And then as you can see here, we have created one bucket here, the VSRN S3 bucket, and we click on it. We can see that there are a few data informations and of the car info that are being processed in the Amazon SageMaker, and then it will be directed to the Lambda to process again to transfer it into the JSON file here. So we can click on the buckets and then to create a bucket, and then you can see that there are a few buckets that we have uploaded here. And then next we will go to the QuickSight, where the Amazon S3 bucket, the JSON file will be sent to the QuickSight for analysis. So you can type QuickSight and then click on it. It will direct you to the home page of this, and we will click on the analysis here, and it will direct you to the particular car info analysis. So actually, we can visualize our S3 bucket information here, where there are a few field lists that we can create our own field list to create a analysis that we can see it to actually more visualize what we are going to do. So we are going to take this sensor time in y-axis and battery condition, where is a summation per hour in 1 day that being sensed by the sensor in the IoT devices, and the IoT devices will send it to the IoT core for the transfer of the data to the SageMaker, and then the SageMaker will store it into the S3 bucket after being processed, and we can visualize it using the QuickSight. As you can see that every hour it will record the sensor time, where it is the sensor will detect the battery condition per hour. So that's all from my presentation. Thank you.
And now I'll be talking about the notification module that we implemented for the project. As shown here in the architectural diagram, the notification module receives event message from a designated S3 bucket in which SageMaker result outputs to. This event message is triggered in such a way that any create or put event from the S3 bucket are going to invoke the Lambda function. After that, the Lambda function will then check if the event message object that is put in the S3 about their label condition. In a sense, if the prediction label that is outputted or processed by the SageMaker result in positive, then the rest of the Lambda function will proceed, in which the rest of the function covers and processes the event message to be sent to a subscribe account in one of the SNS topic. If not subscribed, then the notification would send a confirmation message instead. After processing the message into a readable format, it would then send out the email to the vehicle owner's subscribed email, in which can be viewed from any device accessible to the email communication channel. And now I'll be presenting the notification module we implemented as in the AWS console. First of all, we start at the S3 bucket, specifically the VSRN S3 bucket, where the SageMaker result outputs to. The objects here are saved as JSON type. Now, whenever any create or put event is initiated, this specific Lambda function is triggered, so-called the VSRN emailed. This VSRN email Lambda function will receive the event message from the S3 events and process it accordingly. The event message received will be the stream information from the S3 object. The details of the JSON object is as follows. The prediction label attribute is what the SageMaker process outputs. Now, if the SageMaker prediction label result in 0, it will process the data furthermore, or else it will just stop there. Now, if the prediction label is 0, as mentioned, the message will be processed into a more readable format. As such, in this case, it will be an email format that will be shown later. This section of the function would check for the existence of the subscription in the SNS topic by matching the JSON data email right here. If not exists, then it will invoke the SNS subscribe function for the email and awaits confirmation message. After that, this following section will then publish the message via email channel to the vehicle's owner's own email. For example, in this SNS topic, there will be a subscription as such already made here. And the details of the email notification are sent as shown here. Battery anomaly detected with vehicle ID attached, time when the message is sent, and battery resistance, voltage. All these components are, let's say, health conditioned. And that would wrap up our overall presentation of the project. Thank you.